In this video, we show how to design the structure supporting surface optical waves on the surface of a one-dimensional photonic crystal. So, there are waves propagating along the surface, and these waves are bound to the interface by total internal reflection from the external medium on the one side, and by the band gap of the photonic crystal on the other side. The program can calculate them at any predetermined wavelength and at any predetermined angle. For example, we will work with the external environment, which is water. And in order to get an angle greater than the internal reflection, we take ρ equals 1.35. For the refractive indices of materials in the structure at different wavelengths, we choose their Sellmeier formulas. The program will simultaneously calculate the optimal thicknesses of these alternating layers D1, D2, and the thickness of the third layer, D3, which will support surface waves at a given wavelength and at a given angle. At step 2, we set the optimal number of layers. Let us make sure that for given losses in the structure, this number of layers is optimal, that is, the resonant dip of the reflection coefficient drops almost to zero. Also, let's make sure that we got the resonance exactly where we expected. We see that the angular resonance is exactly at ρ equals 1.35. The propagation length of this surface wave is 336 microns. We also make sure that this resonance is at the wavelength we expected. One can see that the resonance wavelength is about 633 nanometers. We can also look at the dispersion of this structure. It is like this. This is the band gap, and this is the surface mode, which is really present at a wavelength of 633 nanometers and at ρ equals 1.35. We can return to step 1 and change the thickness of the final layer. Now we take the second thickness to obtain two surface modes. Then for the taken thickness we will see that the dispersion has the following form. Here again we have a band gap and we have two modes, one of which is still at a wavelength of 633 nanometers and at an angle ρ equals 1.35. How one can use two surface modes, for example, in optical biosensors, you can read in the article, the link to which is given in the video description. We can look how the field distribution of these modes differs. This is the first mode and its spatial field distribution. And this is the second mode and its spatial distribution of the field. That's all. In the next video, we will show how to count surface waves when the final layer is metal. It will be p-polarization.